So the main objective of this project is to present deep learning based object detection framework based on convolutional neural networks and regressive convolutional neural networks. To understand images, I classified and concentrate on classifying different images, but also try to precisely estimate the concepts and locations of objects contained in each image. The task is referred as object detection, which normally consists of different subtasks such as face detection, pedestrian detection, and skeleton detection. Regressive convolutional neural networks algorithms. They use regions to localize the objects in images. High-scoring regions of the image are considered as object detected, so the algorithm follows a different approach. It applies the neural network to the entire image to predict bounding boxes and their probabilities. High probabilities of the image are considered as objects detected. Other techniques are also used, such as transfer learning, which is a technique to reuse the weights in one or more layers from a pre-trained network model in a new model by keeping the weights, fine-tuning the weights, and adapting the weights totally when training a new model. Object detection is able to provide important information for semantic understanding of images and videos, and is related to various applications including image classification, human behavior analysis, face recognition, and autonomous driving. While inheriting from neural networks and related learning systems in the fields that I have presented in this video to develop this project for neural network algorithms. The problem definition of object detection is to determine where objects are located in a given image, such as object localization, and which category each object belongs to. For instance, object classification. Therefore, the pipeline of traditional object detection models can be mainly divided into three categories. That is informative region, selection, feature extraction, and classification. Feature extraction. In order to recognize different objects, the model needs to extract visual features that can be provided as a semantic and robust representation, such as shift, hug, and like features. The classification is needed as a classifier to distinguish a target object from all other categories and to make representations more hierarchical. In this application, I present and illustrate a face detection mathematical algorithm and software program based on Python, which is essential to many face applications and acts as an important pre-processing procedure to face recognition, face synthesis, and facial expression analysis. This is different from generic object detection. The task is to recognize and locate face regions covering a very large range of scales, 30 to 300 PTS versus 10 to 1000 PTS. At the same time, faces have their unique object structural configurations. For example, distribution of different face parts and characteristics like skin color. All of these differences lead to special attention to the current project at task. So large visual variations of faces, such as occlusions, pose variations, illumination changes, impose fantastic challenges for these real applications. The numerical NumPy, NuNPy, is the library equipped with useful resources that make Python into a powerful scientific analysis modeling tool. It is primarily built with Python and uses Anaconda, Spider dependencies for data transformation, number crunching, and to generate the estimates. The library empowers Python with data structures to perform multi-dimensional arrays and matrices calculations. Artificial intelligence, face and object recognition, face detection, and picture or video recognition is a relevant subject matter of research and development in biometrics. In this video presentation, I will illustrate the AI methodology and framework for the use of face and object recognition application authentication. The key principal component analysis is the statistical method under the underlying heading of factor analysis. The objective of the principal component analysis facial recognition system is to reduce the large amount of data storage. The two-dimensional face recognition PCA principal component analysis is based on information theory concepts. It seeks a computational model that describes a face by extracting the most relevant information contained in that face. The three-dimensional face recognition paradigm consists of 4 modules: the device module, the data processing module, the feature extraction module, and matching engine module. The device module acquires initial 3-dimensional facial data.
while the data processing module performs image filtering. The feature extraction module receives the optimized three-dimensional surfaces for further feature vector analysis. So, my main objective is to present a software algorithm written in Python based on a robust framework and a platform consisting of a face recognition training algorithm, a D library, the NumPy, N-U-M-P-Y, the OpenCV, Python. And in addition to using Anaconda development tool for analytical purposes with Spider to show the proper results of the algorithm in play. So first encode the face, then encode the image, then perform the face classification.
In this application, I present and illustrate a face detection mathematical algorithm and software program based on Python, which is essential to many face applications and acts as an important pre-processing procedure to face recognition, face synthesis, and facial expression analysis. This is different from generic object detection. The task is to recognize and locate face regions covering a very large range of scales, 30 to 300 PTS versus 10 to 1000 PTS. At the same time, faces have their unique object structural configurations. For example, distribution of different face parts and characteristics like skin color. All of these differences lead to special attention to the current project at task. So large visual variations of faces, such as occlusions, pose variations, illumination changes, impose fantastic challenges for these real applications. In this project, I illustrate the design and development of the three-dimensional face recognition system. The three-dimension is a class of methods that work on a 3D data set representing both face and head shape as range data or polygonal meshes. The device module acquires an initial three-dimensional facial data and transfers this information to the processor. The data processing module reconstructs the 3D surface for further recognition. The feature extraction module builds the feature vector, which is a biometric template based on three-dimensional surface reconstructed for further use in the matching process. The matching engine module provides a comparison of acquired and previously enrolled biometric template. The description of the compact biometric template extracted 2 to 4 kilobytes, and the description of the face shape in 3D face geometry. which includes full features description, ground-based measurement, you only look once. The YOLO consists of 24 CONV layers and 2 FC layers, of which some CONV layers construct ensembles of inception modules with 1x1 reduction layers, followed by 3x3 conversion layers. The network can process images in real time at 45 FPS, and a simplified version of fast YOLO can reach 155 FPS with better results than other real-time detectors. YOLO produces fewer false positives on background, which makes the cooperation with fast, regressive, convolutional neural networks become possible. The YOLO version 3 and version 2 adopts several impressive strategies such as BN anchor boxes, dimension cluster, and multi-scale training. The SSD YOLO has difficulty in dealing with small objects in groups and causes strong spatial constraints imposed on bounding box predictions. The SSD takes advantage of a default anchor boxes with different aspect ratios and scales to discretize the output space of bounding boxes. That is to handle objects with various sizes. The network fuses predictions from multiple feature maps with different resolutions. So SSD adds several feature layers to the end of the network, which are responsible for predicting the offsets to default boxes with different scales and aspect ratios and their associated confidences. The network is trained with a weighted sum of localization loss, smooth LI, and confidence loss such as softmax, which is similar to the final detection results are obtained by conducting NMS on multiple scale refined bounding boxes.